In this video, we will discuss the recent paper titled CNT, Conditioning on Noisy Targets, a New Algorithm for Leveraging Top-Down Feedback. This paper was published in October of 2022 and is a work by a collaboration from University of Montreal, Microsoft Research, and Google Research. In a nutshell, they propose a novel regularizer for the task of supervised learning. So the objective of this paper is again focused on, for example, let's say classification or some sort of a supervised learning setup. So they propose a regularizer for it, which they call it CNT, which is the abbreviation for conditioning on noisy targets. The goal is that they would basically modify the target and use it as a hint for the model and basically alter this hint in order to sort of enforce the easiness or difficulty of the task by, for example, if you have the target, the model can somehow cheat. And therefore, it's important to note what happens at the inference or testing time. In that case, they do not know the target, and then they run the network with only noise in place of the noisified target. So there's no cheating in the test set. While in training, these hints or these noisified targets can be used by the model. They mentioned that this approach has two main benefits. The first one is that these top-down feedback, and top-down means that you're giving like the label itself, allows the model to focus on simpler or more digestible solved problems. And the second one they mentioned, let's read this together. Rather than learning to solve the task from scratch, the model will first learn to master easy examples with less noise while slowly progressing towards harder examples. Now this part might, be sort of confusing because, for example, in the paper ELR, and this usual observation or assumption is almost, in many cases, true that the model first focuses on, learning easy samples and then progresses to hard and noisy samples. So that on its own is sort of true. Now, in this case, what they basically mean is that this sort of allows you to enforce sort of artificial easiness and, in general, kind of lets you utilize the entire data set. So rather than, let's say, ignoring the hard examples, you still use those hard examples, but this time you also have like a hints from the target, and the model can utilize that in order to achieve better results. One other advantage of this general approach is that introduction of the noise to the system is also associated with, let's say, a lot of noise-based regularizations, and generally that sort of notification has been shown to be advantageous in many cases as well. The works related to this objective is first of all the category of curriculum learning, then the gradual transfer learning, in which you move from easier to harder data sets. There's also the progressive growing, which consists in growing the neural network over time to replicate neural growth, or again to focus on easier tasks rather than solving harder tasks. Now again, they mentioned that their objective is to seek to help the model to progress from easier to harder tasks by providing it hints during the training. Now, one question one might ask is that intuitively, why do they expect that this approach would work? They mentioned that, okay, given the strong evidence that the progressive learning methods have demonstrated, they believed that providing these types of hint to the network would have also improved the generalization in the supervised learning setup. Therefore, the evidence for the advantages of progressive learning is basically the intuition as to why this methodology should work. In this example, you can see what these types of noisified targets are. For example, let's say you have a label cat and you have a label dog, so you can have like these types of noises. As you can see, the t equal 0.1 is a small noise. Therefore, when you look at the distribution, you can easily infer that this target was actually a cat. Therefore, for example, if a model gets this in the training time, it can cheat. And as you increase the noise, it becomes more and more like these indistinguishable distribution. And for the inference, you just purely deal with noise. Therefore, there is no information as to what the label is. Therefore, it's a valid validation scheme. So the question that they try to answer is that how can one provide hints about the solution to a neural network? Again, the advantage of introducing hints to a neural network is that it can sort of adjust the difficulty of the overall task and how much to focus on an example. So in some sense, you could see that it's implicitly weighing the items in terms of their importance in some sense. The way they define a solution for this problem is that they propose to give hints to the neural network by conditioning the neural network on a noisy version of the target. For example, the target could be actions in an imitation learning or labels in a classification. Now, this conditioning sort of, makes people wonder about things such as the style GAN, and as we go forward, we can see that actually there are a lot of things from that type of idea which is used in this case as well. The advantage of this hint introduction is that it provides a path for the neural network to learn to solve the easier problems, meaning that the items in which the noisy target has less noise, before harder problems. One other justification from the standpoint of cognitive science is that, for example, it's the role of top-down feedback seemed to be prominent. For example, they mentioned that a person may be able to navigate a dark room that they are familiar with, in other words, they have hints about. By leveraging the priors, again, those hints about where the objects are expected to be present. One important detail about the work is that instead of progressive approach, meaning you're starting from, let's say, less noise or to higher noise, they take a multi-scale approach. Now, what's that? So an example of the multi-scale approach they mentioned is the multi-scale gradient, or MSG work. And they do that because MSG is also used in the style GAN version 2 as well, rather than progressive growing. And it was shown empirically to enhance the stability and quality of the generated samples. So they mentioned that the main benefit of the multi-scale approach is that the model is given gradient at all levels of difficulty. So again, at all levels of difficulty. Now, what is the advantage of that is that as you're directing the model to perform a certain action, it cannot unlearn solving the simpler tasks. For example, in the case of the style GAN generating lower resolution images with MSG, after learning to solve the harder tasks. So again, you sort of want to retain the information about the easier samples as well. The way they do this noisification is that they sample uniformly from a continuous noise level, T, from a uniform distribution between 0 and 1, where T equals 0 means no noise and T equal 1 means only noise. So this type of noisification, we will talk more about it. And then they inject an embedding on the noise level and the noise label. So you have the noise level and the noisy label. Both of them are kind of providing this hint to the model. And at test time, obviously, they only have like one, meaning that they only just work with noise to provide a hint. As mentioned before, they call this CNT. Now, the advantage of this approach is that it's easy to implement, only requires adding a small embedding, and doesn't, add a lot of parameters to the model, and also requires a minimal change to the structure. So, given a supervised learning setup, you usually have basically the empirical risk minimization, or some sort of a supervised learning loss, such as this, and the focus is to make this objective as minimum as possible. This picture here also showcases something. So if you, for example, take Cypher 100, and if you take the top 1 and top 5 accuracy, the green one be the no noise examples, in other words, forcefully easy examples, and forcefully easy examples, no noise, all the way to 1, which is just usual, no hint about like the system. As you can see, as you go forward through time, which is the x-axis here, which is the epochs, the green one goes on the top first, which means that the no noise or the forcefully easy examples are learned first, and then you can see that these red and blue ones are going up. So this is some sort of a interesting empirical observation as well, shedding light on the ideas and intuitions behind this work. Now, in the supervised setup, L can be an arbitrary loss function. F of theta is a neural network which is parameterized by theta. X and Y are a pair of data and target sampled from a dataset. And you could consider Y or the objectives to be real value vectors. C, you can have a number of classes. L would be the number of labels. And therefore you have like a one-hot representation of X. Now, in the supervised setup, what you want to essentially return is the conditional expectation of the Y or the objective given the observation, which is X. So given this distribution, you sort of want to deal with this. Now, in this proposition, instead of having the Y being like the actual non-noisy target, they consider it a noisy target. And then you have this noise level T as well, which means 0 is just the target itself and 1 is pure noise. For the noisification procedure, they basically follow the recent developments in the diffusion schemes. And so let's read it together. Following the recent success of score-based diffusion model, they chose to gradually corrupt the target over time using a diffusion process. So this is the diffusion process that they consider, and basically WT is the Wiener process, which is used in discussions of Brownian motions. Following the empirical evidence from the variance preserving process, again in the context of score-based diffusion models, they used it for the diffusion process, and it's defined like this. So, given that y, or the actual non-noisy target, is y0, yt is sampled like this from this variance-preserving Gaussian distribution. They note that it's also possible to use Laplace distributed noise instead of the Gaussian distributed noise, and it could have some advantages and some disadvantages. For example, Laplace distribution has heavier tails, and it has a higher concentration at its means. So these two distributions, or any other distribution that can be used in here, would sort of dictate at what level the model would be able to sort of infer the label from the noisified target, and what kind of characteristics does that distribution would have, and how would it impact the results. And when they choose the Laplace distribution as well, just to kind of study it as an alternative to the Gaussian, they use this equation over here. Now, in the context of CNT, rather than solving the usual supervised learning problems, they want to also condition it on the noisy target as well. In other words, the loss that you're trying to minimize, you are basically, okay, so you take the model, let's say your neural network, the X, which is passed to it, condition on yt and t, noise level and the noisified target, it would basically result in an inference that is going to be checked against y. Note that at the optimum point, the neural network is expected to know the conditional expectation of y given x. So if t is 0, you know that the response, the returning value should be y0, and if 1, it should be completely ignored. And as mentioned in the test time, you use the t1 in order to just prevent any sort of hint from the objective. Now, this is the structure of the network. As you can see, it could remind you of things such as a style GAN. The idea here is that you have a noise level T, which you normalize and pass through the Fourier embedding in order to kind of keep the high frequency components. The target Y is going to go through that diffusion process with this noise level, and both would go through this type of fully connected pipeline. They will be concatenated, so these two representations will be concatenated. It forms an embedding for the noise, and then at each level it would go through a fully connected, and then will be applied to the normalization in order to make the representation conditioned on noise and target as well. So to recap, this approach, the approach that they use is conditional normalization layers, which was used in, let's say, the style GAN as well. This approach starts by processing T, Fourier embedding, increase the high frequency signal, and then all the other steps that we just discussed. Again, note that the model should learn to ignore yt when t is equal to 1, given that noisy target contains 0 information about the target at that level of noise. Now, I'm not going to go through all of the related works discussed in this paper, but it's just important to know what categories of works were pertinent to this specific objective. So the first thing is leveraging the top-down feedback. So, for example, there are works such as generating an image by using the description that is provided, and so this specific domain is very, very relevant. As discussed in the review of the introduction section, we have the curriculum learning and progressive learning, which is also very relevant. Then there's all the works that have to do with injecting noise into deep models, let's say for regularizations and stuff, and again, because of the heavy presence of noise in this paper, it's also a very relevant category of work. And lastly, the concept of denoising generative models. And the reason why is that CNT can be seen as a model for denoising the target conditioned on the input, which is a very interesting and a novel formulation for the supervised learning context. So they test this scheme over a wide range of problems, including image classification, relational reasoning, equilateral versus non-equilateral shape classification, which again is a classification problem, and reinforcement learning. One other thing that they test is the noise-only condition, meaning beta min equal beta max in the variance preserving process, so that for any t it's a pure standard Gaussian noise. because it's also important ablation study to kind of figure out what portion of this improvement is due to just the presence of noise and sort of noise-like regularization, and what part of it actually has to do with the providing of hint to the model. As for the activation, they focus on the mesh activation, which provides certain additional regularization and has a set of better characteristics that makes the training more optimal. They show, for example, in the table above, that it generally leads to slightly better results. All right, for the classification, to focus on Cypher 10, 100, and Tiny ImageNet and ImageNet. So the details of optimization is here. Dropout P equal 0.1, alpha equal 1 for mix-up. SGD is used with a momentum of 0.9, learning rate of 0.1, and VTK of 1 E minus 4. And learning rate schedule was basically decreased by a factor of 10 at 50% and 80% at the training time, with some differences for the Tiny ImageNet, which are discussed in here. All right, so for classification test accuracy, average test accuracy on baseline, meaning just supervised setup with the descriptions that was given before on the the models and the training setup and everything. Only noise, which is just the beta min equal beta max, and CNT, which means you're providing the hints. You can see that it generally, so in the case of Tiny ImageNet, it seems to be the baseline is very close, or in this case, for example, better than these two. In the case of Cypher 100 and Cypher 10, you can see, for example, in Cypher 10, the noisified version is actually the best one. And in the case of Cypher 100, it's also, again, very, very close. So in this table in particular, I see a very minimal improvement, if any, and this is here. Now we go to low capacity classification. So we have Cypher 100, and Tiny ImageNet, and Tiny ImageNet. This time you can see here that, for example, for the case of ResNet 9 on Cypher 100, you go from 72 to 71 if only using the noise version of it, but you go to 74 if you provide the hints. For the case of Cypher 100, what you can see here is that, in general, if you, for example, consider the CNT to be the effect of only noise plus hint, the only noise is actually leading to a lot of improvement over the baseline. So 44 becomes 53, and then with the providing of hints, it becomes 54. So 57 becomes 63, and with providing hint, it increases 0.1%, and with a little less variance in comparison. For the case of Tiny ImageNet, the only noise seems to be better, and for the case of So all in all, generally the CNT seems to be the better approach. For the equilateral shape detection also, you could see that the CNT is sort of consistently better than the others. So the other task is the task of detecting equilateral shapes. So they, for example, consider equilateral triangle detection task from this paper, and they also add other shapes to it. They describe their process in this section of the paper. And more of the details as to the modeling and everything is provided here. For example, they frame this task as a classification task. You have two classification heads, one detecting whether or not the shape has 4 or 3 sides, and the second head is going to denote whether the given shape has equal length sides or not. And then the details of training and everything is brought here. And again, the results are shown here, showing that CNT is generally doing better. One other interesting finding in this shape detection task is that they figured that, let's read this part together. Training converges in very few epochs at low noise level. At higher noise level, training requires more epochs to converge, and more smooth, transition between these two regimes. The other task that they validated on is the sort of clever task, which has to do with relational reasoning tasks. So in this, each image is a 75 by 75 image, and you have also a question. So this task has 3 types of questions: unary, binary, and ternary. And for example, the unary questions have to do with a single object, such as what is the color of the square, and things like that. Now, one important thing is that in modeling this thing, because you also have the question as well, they also injected the question embedding along with the label in order to sort of condition the outputs on the question as well in order to generate, in order to get to the final classification. And lastly, they focused on the reinforcement learning with decision transformers as well and evaluated the CNT on the Atari benchmark. You can see the result of the sort of clever task in here. You can see that The CNT seems to be doing pretty good. But again, the improvement doesn't seem to be super huge. So you can see here, for example, let's say, for example, ResNet, the ternary tasks, and so the model is ResNet, the task is ternary. The baseline is 74, only noise 76, CNT is 74.8. Just doing better than the baseline. But yeah. And then for the case of decision transforms, also the results seem to be good. They also did experiment with Laplace distribution and basically report the results here. And yeah. So you can see that depending on the distribution that is going to be used in place of that Gaussian or Laplace, then depending on the characteristics that it would exhibit, it could have different impacts on the training. And they actually mentioned this as one of the sort of limitations in this work as well, because they only tested one way of conditioning on a noisy target, which is one part of these limitations, and the other one is that other types of noise other than Laplace and Gaussian can also be tried. And this concludes our discussion of the paper CNT, which was a pretty interesting article. Thank you.